Hi guys, this is Bhavya and today I'm going to be explaining switching techniques in computer networks. Before we begin today's topic, I want you to think about something simple. Every time you send a message, join a video call, or open a website, data travels through many devices before reaching its destination. But how does the network decide which path to take? How to handle multiple users at the same time? How to avoid chaos? The answer is switching. In computer networks, switching is the technique used to connect a source to a destination through intermediate network devices called switches or nodes. Switching helps the network in managing traffic, sharing resources, and ensuring communication is possible at large scale. Without switching, modern networks simply could not exist. There are three major types switching techniques we will study today: circuit switching, datagram packet switching, virtual circuit packet switching. Let's begin with circuit switching. When you look at the circuit switching diagram, notice how structured it is. You see senders on one side, receivers on the other, circuit switches in between. When communication begins, the network does not send data immediately. Instead, switches cooperate to create a single continuous path from source to destination. Once this path is created, it is locked. No other communication can use it. All data flows through the same route. Even if there is silence, the path still exists. This diagram shows a one-to-one relationship between communication and network resources. Now, for example, let's take Ria wants to talk to her grandmother using a landline phone. She dials the number, and before any voice is heard, the telephone network creates a private path connecting both phones. This path is reserved only for them. No one else can use it. As Ria speaks, her voice travels smoothly along the same fixed route without delay or interruption. Even when she pauses, the path remains occupied. When the call ends and the phone is placed down, the network releases the path, making it available for others. This is circuit switching, a dedicated connection established before communication and released after it ends. Advantages of circuit switching. Now let's understand why circuit switching was used for so many years. Number one, guaranteed bandwidth. Once the circuit is established, bandwidth is fixed and predictable. Number two, no packet loss. Data is transmitted continuously, not in packets. Number three, constant delay. Very important for voice communication. Number four, high reliability. Once connected, communication is very stable. This is why traditional telephone networks relied on circuit switching. However, circuit switching has serious limitations. Number one, inefficient resource usage. Even when no one is talking, the path is reserved. Number two, setup delay. Communication cannot start instantly. Number three, poor scalability. Not suitable for large data networks. Because of their drawbacks, newer techniques were developed. Now let's move on to datagram packet switching, the backbone of the internet. Look carefully at the diagram. You will notice multiple sources, multiple intermediate nodes, packets labeled A1, A2, A3, B1, and B2. Each packet is treated as a separate entity. There is no predefined route, no memory of previous packets, no guarantee of order. Each node independently decides, where should I send this packet next? This makes the network flexible, dynamic, adaptive to congestion and failure. This diagram visually shows freedom of movement for packets. Now let's take an example. Arav wants to send a long message to his online friend. The message is first broken into many small packets. Each packet is given the destination address, like writing the same address on many postcards. There is no fixed path. Each packet travels independently through the network, choosing the fastest available route at the moment. Some packets arrive early, some arrive late, and a few many even take different paths. At the destination, all the packets are reassembled in the correct order. This is datagram packet switching. No dedicated path. Each packet decides its own route. Datagram switching is extremely powerful. Number one, efficient bandwidth usage. Links are shared by many users. Number two, highly scalable. Works for millions of devices. Number three, fault tolerant. If one path fails, packets choose another. Number four, no setup delay. Communication can start immediately. That's why the internet uses this technique. However, this freedom comes at a cost. Number one, no delivery guarantee. Packets may be lost. Number two, packets may arrive out of order. Reassembly is required. Number three, variable delay. Not ideal for strict real time applications. So, datagram switching prioritizes efficiency over reliability. Now, let's discuss virtual circuit packet switching, which balances the previous two methods. Observe the diagram carefully. You can see a virtual connection. Packets numbered in sequence, the same route followed by all packets. Before transmission, the network decides a logical path. This path is stored in switches. During transmission, packets follow this remembered route. Order is preserved. After communication, the virtual path is removed. This gives control without physical reservation. Now let's take a look at the example. Mira wants to send a large file to her friend. Before sending the file, the network first decides a logical route from Mira to her friend and remembers it. This route is not a physical wire but a virtual path. Now the file is broken into packets, and all packets follow the same decided route, one after another. Because they travel on the same path, they arrive in order. When the file transfer is complete, the virtual path is removed and the network resources are free. This is virtual circuit packet switching. A logical path is set first, packet follows it, and then the path is released. The advantages of virtual circuit switching. Number one, ordered packet delivery. That is, no reordering is required. Number two, better quality of service, more control over routing. Number three, more efficient than circuit switching, no permanent reservation. Number four, lower delay variation compared to datagram switching. The disadvantages of virtual circuit switching. Setup number one, setup phase is required. Communication does not start instantly. Path failure affects communication. Rerouting is complex. Number three, more complex implementation. To conclude, circuit switching offers guaranteed performance. Datagram packet switching offers maximum efficiency. Virtual circuit switching offers a balanced approach. Modern networks choose the switching technique based on types of data delay requirements, reliability needs. Understanding switching techniques helps us understand how real world networks operate. Thank you. Circuit switching is a switching technique in which a dedicated physical communication path is established between the sender and the receiver before any data transmission begins. This dedicated path remains exclusively reserved for the entire duration of communication and is released only after the communication ends. The operation of circuit switching takes place in three distinct phases. The first phase is the circuit establishment phase, where the network identifies a suitable path between the source and the destination and reserves the required resources such as bandwidth and switches. During this phase, no data is transmitted. The network only focuses on setting up the communication. Once the circuit is established, the system enters the data transfer phase. In this phase, data flows continuously from sender to receiver through the fixed path. Since the route and resources are already reserved, there is no delay variation, no packet loss, and data arrives in the exact order in which it is sent. This makes circuit switching highly reliable for real time communication. The final phase in the circuit, termination phase, where the communication ends and the reserved resources are released back to the network for use by their connections. Circuit switching was primarily designed for voice communication where continuous and uninterrupted transmission is essential. Traditional telephone networks are classic examples of the circuit switch networks. However, circuit switching has major limitations. If the user remains silent, these reserved resources still remain unused, leading to inefficient bandwidth utilization. Additionally, the setup time before communication begins introduces delay, and the approach does not scale well for modern data networks. Despite its inefficiency for data transfer, circuit switching remains important for understanding the foundations of network communication. Datagram packet switching is a connection-less switching technique in which no dedicated path is established between the sender and the receiver before data transmission. Instead, the data is divided into small units called packets, and each packet is treated as an independent entity. In this technique, every packet contains the complete destination address, allowing it to travel through the network independently. Routers in the network do not reserve resources or remember previous packets. Instead, each router makes a routing decision for every packet based on current network conditions such as congestion and availability of paths. Because of the independence, packets belonging to the same message may take different routes, experience different delays, and arrive at the destination out of order. Some packets may even be lost during transmission. The responsibility of reordering packets, detecting losses, and requesting retransmission is handled by the higher layer protocols such as TCP, not by the network itself. The major strength of the datagram packet switching lies in its efficient utilization of network resources. Since no resources are reserved, bandwidth is shared dynamically among multiple users, making the network highly scalable and flexible. This design also provides false tolerance. If one path fails, packets can automatically be routed through alternative paths. However, datagram switching does not guarantee delivery, order, or delay. This makes it unsuitable for applications that require strict quality of service, such as real time voice communication. The Internet is the best known example of the datagram packet switch network. Services like email, web browsing, and file downloads rely heavily on the technique due to the robustness and efficiency. Datagram packet switching represents a design choice that prioritizes scalability and flexibility over strict reliability. Virtual circuit packet switching is a hybrid switching technique that combines features of both circuit switching and datagram packet switching. In this approach, a logical connection known as a virtual circuit is established between the sender and receiver before data transmission begins, but the physical resources are not permanently dedicated. The operation of virtual circuit switching also occurs in three phases. During the setup phase, the network determines a logical path during the source and destination. This path is identified by a virtual circuit identifier, which is used by all packets belonging to that connection. Once the virtual circuit is established, the system enters the data transfer phase. The data is divided into packets similar to datagram switching. However, unlike datagram switching, all packets follow the same predetermined route, ensuring that they arrive in the correct order. Because routers recognize the VCI, routing decisions become faster and more predictable. After the transmission is complete, the termination phase occurs, during which the virtual circuit is removed and the network resources are released. Virtual circuit switching offers better quality of service compared to datagram switching since the path is predefined. The network can provide control delay, reduced packet loss, and ordered delivery. At the same time, it is more efficient than circuit switching because physical resources are shared among multiple virtual circuits. Despite these advantages, virtual circuit switching still has drawbacks. The setup phase introduces initial delay, and if a failure occurs along the chosen path, the entire virtual circuit may need to be re-established. Technologies such as ATM, frame relay, and MPLS use virtual circuit switching, making it highly relevant in the modern high speed and enterprise networks.